So I'm Bekki. I'm visiting this week. I'm a faculty member at Penn State in the astronomy department, and I study exoplanets. So I'm going to be continuing from where Eric left off last week about modeling exoplanet time series. And I wanted to show you this reference. This is a site that I made for my class last fall, which was a graduate seminar about exoplanet time series. So the seminar was very much focused on reading and analyzing recent papers. Oh wait, I guess I have to move this over. So we have a paper library and some slides. Each lecture I'd do a mini lecture, and then we'd discuss an interesting exoplanet time series paper. So if you get really excited about exoplanet time series and you want to check out some of the literature on the topic, this website could be a good resource. The slides themselves are more focused for astronomy background students, so those may or may not be appropriate for people here. The statistics in particular may be a little too simple. Oh, there is one astronomy student. Okay. All right. So last time, my understanding is that Eric gave you an overview of exoplanets and history about when and how they were discovered. He focused a lot on the radial velocity technique, and he talked a lot about how to fit those data sets and different approaches people have been developing to fit them in a better way and get out better parameters for the planets. And also, he talked a bit about the detection criteria, like how do you know that you actually found an exoplanet and it's not just noise or stellar activity. And then excitingly, today, there was a recent exoplanet announcement. 1 p.m. today was unembargoed, of a dwarf star, so a very low mass, cool star that has 7 planets, and many of them are Earth-sized, and at least a few of them, based on their distance from the star, they could have liquid water on the surface. And based on their sizes and their masses, they seem to be a potentially rocky planet. Like they're not a planet like Jupiter where you wouldn't be able to stand on the surface of it. So this is exciting because this is actually something that we could follow up with new space telescopes that will launch soon, like James Webb, and study the atmospheres and see what's the atmosphere made of, and even look for a biosignature like oxygen that could indicate that there's life here. So this is really great because it now has this really great target for us to study further, where we know that there's planets that at least could be like Earth that have the right properties to maybe have life on them. So that's why it was very exciting to hear about this today. So we can come back to this. We can even take a look at some of the data in a little bit. But I wanted to give you an overview of how I'm going to lay out the class today. I'm first going to tell you about other exoplanet detection techniques, including the transit technique, which was used to detect the planets that I just showed you. Some of the challenges we face with exoplanet time series, and more about the transit technique and photometric time series and how we deal with issues that come up in that type of time series that are preventing us from getting the properties of the planets that we want. And we'll have a break about halfway through. So I'm thinking this will be about halfway through, but I want you to feel free to ask questions. So if we don't end up getting through all the things that I prepared, that's perfectly fine. And we'll just take a break at around 5:15-ish, even if we haven't quite gotten through all these things. So I first want to give you a brief overview of other exoplanet detection techniques. I would say that every detection technique has time series challenges, though they're all a little bit different. And so I'm going to just show you what those other detection techniques are. And then I have a fun activity that's going to have you look at some real exoplanet data sets to sort of get a feel for what they look like. So last time Eric told you about the Doppler technique. That's where you detect the radial motion of the star not only is the planet orbiting the star, but the star is doing its own little orbit around the center of mass. And by looking at the spectral lines, we can see Doppler shifts that tell us if the star is moving towards or away from us. And this gives us the mass of the planet. The transit technique, which is going to be a focus today, particularly in the second half, and that was used to find those planets that were announced today, is where a planet goes in front of the star and blocks the light, and you see a dip in the stellar brightness. You can't actually resolve or see the surface of the star. You just measure the total amount of light. But since the planet is much colder than the star when it passes in front, it makes the brightness go down. And one thing that I like about this particular cartoon is that even though it's like a NASA cartoon that's meant for public outreach, it's kind of realistic in that you can see that the star is not a uniformly lit surface. It's dark around the edges, and then it has patches on it from all the different stellar variations going on. And you can see the light curve is not perfectly flat. It has all these wiggles in it. So that's going to be the big challenge that we talk about in terms of trying to get a good measurement of the signal, particularly when it's not a nice big signal like this, but more on the borderline of what we can detect. So these are the transit light curves for that newly discovered system. Going from the inner planet, which has an orbital period of only a day, to the outer planet, which has an orbital period. They're not 100% sure, somewhere between like 10 days and 20 days, because they only saw one of these transits. If you see the planet transit over and over again, then you can measure very precisely what its orbital period is. So like if this is the Earth, every year you'd see the Earth pass in front of the star and you know its period was 365 days. In this case, there's only one transit, so they just estimate by how long it takes what the period might be. The transit technique also gives you the size of the planet, because how much light gets blocked out depends on the planet's size. And it can also tell you about the speed that the planet's moving based on how quickly the transit happens. Yeah?
What are the white dots versus the colored dots?
Those are
that some kind of average?
Those are binned, and I believe that they are, I think they phase them up and then bin them, which is an interesting, that might be a little bit objectionable, but that you see a lot of times.
This looks like a pretty straightforward case of there's a planet, so.
Yes.
Is it recently discovered because people hadn't looked at the data before, or the data is recent, or is there some kind of processing that went into making it look this nice?
Yeah, great question. So this is a fairly straightforward case because this is a really small star. So even though the planets are small, even though the planets are small, the star is so small that it makes a big signal. So this target is such a low mass star that it wasn't part of most surveys. And there's a new survey called the TRAPPIST survey. This is TRAPPIST-1 that's starting to look at a lot of those much cooler stars that are really low mass red dwarfs. And that's why, even though these things only have periods of a few days, so they're orbiting much closer to their star than Mercury is for the sun, they could be habitable because this is such a cool low mass star.
Is it known if they're tidally locked?
They probably are, but we don't have a direct measurement of that. So that definitely can affect their habitability. So tidally locked means the planet's, it's just like the moon, where the planet's day is the same length of its year, so the same side of it is always facing the star. So they had already actually detected a couple planets orbiting the star from the ground, and then they got time with the Spitzer Space Telescope, which is an infrared telescope, and that's where they found these other transits. So it has so far seemed like the more we go down to lower mass stars, the more planets that we find. And that is even statistically significant. So that seems to be telling us something about the planet formation process, particularly for low mass planets. It's very interesting. So then we actually have mass measurements for some of these planets, but not using the technique that Eric talked about last time. It's actually using a different technique, which is called transit timing variations. It's possible that he talked about this too, but it's not the radial velocity technique. So if you have one planet and it's orbiting the star, then every planet year, so every orbital period, you'll see it transit the star, and it happens purely periodically. But if you have multiple planets in the system, particularly if they're near integer ratios like those planets were, then they can disturb each other's orbits. And then instead of the planet transit happening purely periodically, it can be early or late, and that's called a transit timing variation. And since it's caused by gravitational interactions between planets, then you can use it to detect the planet's masses. And if we could see the Earth transiting from another system, if we had really, really good data, then we'd see the effects of other planets in the solar system disturbing the Earth. But those are extremely subtle effects because the other planets in our solar system don't have a really strong effect on the Earth. These effects can be much stronger. They can be minutes or even hours difference from one transit to another. So this is definitely a challenge in that we don't just need to detect this signal. We want to measure exactly where the central time is and see if it's shifted from transit to transit. And sometimes we also want to see whether the planet's slowly getting tilted and going across different chords of the star. That's a transit duration variation. I'm not going to talk about it too much, but it's another reason why we're not just trying to detect these transits, we're trying to really get good constraints on all the planet parameters, even though there's noise there. So even though this looks like a clear detection, maybe if we're trying to see exactly where the center of this is, we still have some challenges with the noise there. Another technique that we're not going to talk about too much, but I just want you to know it's out there because it's going to start to be a lot more prolific once some new telescopes launch, is called microlensing. So that's where a planet gravitationally bends the light of background stars. And since the planet system is moving relative to background stars just because of galactic motions, you can see a background star suddenly get much brighter and then dim again because of the effect of the planet. Oh, I didn't realize this was a movie. Well, it's not a very exciting one, but that's what happens. Okay, and then oh no, there's two other ones. There's also direct imaging. So this is where we block out the light from the star and directly detect the light from the planet. And this is actually does have time series problems because we're trying to trace the planet's orbital motion. And this, we can usually only see planets that are really far away from the star, like even like Neptune distance, say. So we're not going to be able to usually see the whole orbit of the planet, but just see a little bit of motion on the sky. But that still gives us a time series data that we can fit. And then finally, astrometry it's kind of like the Doppler technique where we're measuring the motion of a star, but instead of measuring the radial motion, we're measuring the motion on the sky. So we're trying to trace the subtle motion of the star on the sky due to the planet's orbit. And this has been really challenging, but there's some hope that with future space missions that we'll be able to finally be able to use this. But so far, there's not really been a great case of a really reliable detection using this technique, just because it's so hard to measure the star moving by such a tiny amount on the sky. And then one other one, there's pulsar timing. So pulsars are evolved stars that are putting out a radio beam, and so they're spinning around, but if they're being gravitationally disturbed by a planet, then you can see the timing of that pulsar beam sweeping by is not strictly periodic because there's a planet disturbing it. So to give you more of a feel for these data sets and these techniques, I have an activity, and we'll see how this goes. There was some debate over whether statisticians will find this interesting or not. So if we start the activity and people are like, this is boring, then we can move on. But I'm going to distribute, I have 4 envelopes, so some people will want to team up. Maybe you folks can team up. And actually, I'd suggest everyone team up, like even if you have multiple, even if I have too many envelopes, that's fine. You probably want to at least be talking to at least one other person. So what this is, in each envelope, there's 11 exoplanet data sets of all different types: transits, radial velocity, transit timing variation, and then there's 11 sets of planet properties. And to give you a feel for what the different techniques can detect, what the data sets look like, the goal of the activity is for you to match up the data set with the planet that it measured. So, and if you have any questions, raise your hand, because it may be that there's some crucial thing that I didn't explain about the technique that you need to know. Okay, so let's go on to exoplanet time series challenges, which you may have just experienced a challenge because this was a challenging activity, but this is like what statistical issues do we run into when we're trying to deal with some of these exoplanet data sets? And so a lot of times we have a data set like the one that you looked at. We're trying to fit a planet to the data set. So we're trying to get those properties that you see on the card, like what's the planet mass or what's the planet size, depending on what sort of data set it is, and then to get a reliable uncertainty on that. So if it says like period 66.6 plus or minus 0.1 days, we want to be able to get the 66.6 and the plus or minus 0.1 days to be really robust and reliable, because then that in turn will go into our models of how planets form and how planets gravitationally interact. So having good measurements and good uncertainties is really important, but also challenging. And what most people tend to do is to do a chi-squared minimization on their data set. Eric talked about some alternatives last time in terms of computational techniques like using MCMC or variations of that. But I sort of want to go back to the chi-squared statistic itself and say, is it appropriate? Do data sets follow the assumptions there? And if not, how can we modify the likelihood function so that it can actually encapsulate what we know about the data set? So I'm just going to put this up. I'll talk about it more as we go on as an example data set. So this would be like a radial velocity data set that Eric talked about last time. So it's a sinusoidal signal. In black is the reported data and uncertainties. And in red is the model for the data that we're trying to fit. And
what model did you fit here?
Yeah, so here we're fitting a sinusoid. What we're fundamentally fitting is a sinusoid. What's its period, phase, and amplitude? That then translates into what's the planet's mass. Actually, it's, as we talked about, it's its minimum mass, because we're just seeing the projection on the sky, its orbital period, and its orbital phase. But usually what we do, unless we know that there's gravitationally interacting planets in the system, and there's only a couple examples of that, like I think Eric mentioned at least one last time, but normally we can just take this data set and fit a sinusoid to it. And sometimes we can add some harmonics if it's on an elliptical orbit. But for simplicity, we can just start with a circular case and say it's just a sinusoidal signal where we need to find the amplitude, phase, and period of the sinusoid. Okay, so I'm going to start with just I'm sure you all have, I think this is going to be very much a little too simple for you, but that's okay because the exoplanet part is new. How do we go from Bayes' theorem to chi-squared, and what assumptions are wrapped in there? But what we'll really focus on is how are the exoplanet data sets violating those assumptions, and then how can we adjust the likelihood function to be able to deal with that? So Bayes' theorem, we have the probability of the hypothesis given the data, the posterior distribution is the probability of the data given the hypothesis. So that's the likelihood times the probability of the hypothesis. I'll just abbreviate that. This is the prior over the probability of the data. That's the evidence. So when we're fitting a set of parameters to our data set, the hypothesis we'll call a vector x. This is the period, the mass or amplitude, etc. This is all the parameters in the model. And then the data we'll call d. In this case, it's a radial velocity time series. It could be a transit time series or any of the techniques that I mentioned. So the probability of x given the data is proportional to the probability of the data given x times the probability of x. So when we do chi-squared minimization, we're introducing some potentially highly problematic assumptions. The first assumption is that there's a uniform prior. And to give you a hint that this may not be the best assumption, I want to ask you, let's say you haven't even looked at the data yet, and I ask, is it more likely that there's a planet in the data that has a mass between 0 and 10 Earth masses, or between 300 and 310 Earth masses? Jupiter's mass is about 300. Would you say that those two were equally likely, or would you not? So why don't I do a survey? So the three options are going to be, you think it's more likely that it's 0 to 10, you think it's more likely that it's 300 to 310, or you think it's equally likely. So who thinks it's more likely to be between 0 and 10? Okay, who thinks it's more likely to be between 300 and 310? And then who thinks it's equally likely? Okay, and some people didn't vote. Would anyone mind sharing why they chose their answer? Yes.
Yeah, because I didn't have any idea, so.
Yeah. Yeah. So you're saying if you're very ignorant, it's best to use a uniform prior, but is that really true? Is uniform prior the best if you're ignorant?
Well, probably not, because if you like transform the parameter space, then it might not look uniform anymore.
Yeah.
That's like a big problem with like uninformative priors, I guess.
Yeah.
One parameterization looks uniform, but in another it doesn't look uniform.
Yes. Yeah. So that's just from, without even knowing anything about the physics of the problem, we might be worried about using a uniform prior for that reason. Is there a more robust prior we could use if we're really completely ignorant?
Yeah.
I don't know. And like the univariate case, I guess like Jeffrey's prior, right? But
yeah, so it might be better to use something like a Jeffreys prior, and because we don't know, because by saying it's just as likely, saying it's just as likely to be between 0 and 10 and between 300 and 310, like we're ignoring all the log space below that. Like what if it's 0.1 Earth masses or 0.01 Earth masses? There's like so much below 1 Earth mass that we're just sweeping in and saying it's just as likely. Between 300 and 310 just seems like so specific. Like that's, there, of course there's some planets between 300 and 310 Earth masses, but that seems like an awfully specific value. Whereas anything below 10 Earth masses, there's got to be a bunch of planets, at least if we're being completely ignorant, that's what we'd want to assume. So that's just an illustration that using a uniform prior may not be the best decision, and depending on which variable you're fitting, there may be better choices for what to use. And maybe we'll talk more about this when I bring up an example. We'll do sort of a more subtle case where uniform or log uniform, neither one is quite what we will want to use, but that's just sort of to illustrate that a uniform prior may not make sense. Then it turns out as we've looked for planets, we've found a lot more small ones than large ones. But even if we wanted to be completely naive and not use our previous discoveries, it still would be more appropriate to use something like a Jeffreys prior, something that's scale-free, so that we can preserve the fact that there's probably many of orders of magnitude between 0 and 1. So that's one problematic assumption that's often made. And it depends. Like if you have as with everything, if you have a really wonderful data set, it probably doesn't matter whether you're using uniform or log uniform. The issue is when you have, this has actually come up when people discover a planet using the transit technique, so they measure its size, then they try to get its mass by following this up, and they don't really detect anything, or if at best they detect something really weak because they don't have a good enough data set to do that. And then it's like, well, what mass should you assign it? You should use uniform or log uniform. And a lot of times people use these sort of marginal detections to do a statistical population study. And then it really matters what you assumed about what the underlying distribution is in the case where your data is not very good. So sometimes it matters more than others, of course, but we should keep in mind that unless you explicitly correct for it, if you're just doing your fit, you're corresponding to a uniform prior. You can change your variable to be log mass and you've solved it, or you can put it into your likelihood function, but you have to do something to not be using uniform prior. Okay, so then the next assumption that we make is about the uncertainties in the measurements, that the uncertainties are known. So that's like here, there's an error bar that's been reported to us by the person who took the observation, so that the person actually knows what the uncertainty is. That they're independent. They're not there's no correlation in errors from one data set, from one data point to another.
And the uncertainties are all like measurement error uncertainties?
Usually what people give us, yes, is basically how well they could get the positions of the lines. Sometimes it kind of depends on the data set. Sometimes they try to fold in other uncertainties as well. But it's a lot of times just what we have is like we took a limited exposure, so we can't perfectly get where the center of those lines are. And that's the uncertainty that is being reported. So that doesn't account for the fact that there might be stuff going on in the star that's not part of the planet, or like gradual instrumental drifts over time. That's usually not part of our reported uncertainties. But still, a lot of times people just use those reported uncertainties and don't try to fix them in any way. And yes, and that they're Gaussian. So if all those assumptions are true, then you can say the probability of the data given x is 1 over square root of 2 pi You guys probably know this, so you don't necessarily have to write it down. But we'll talk about what this means. So there's k data points. Each has a reported uncertainty, sigma k. So dk is the measured radial velocity. We always assume that we perfectly know the times of measurement, and that's usually a pretty good assumption. Sigma k is the reported uncertainty. And then fk is the radial velocity model. So it's a function of the parameters and of time. So if all these assumptions hold, I think I'll just move over to here. I'm going to erase these names that are no longer. Then the probability of x given the data is proportional to L, and then L is a constant minus chi squared over 2. I'm just defining what I mean by chi squared here. And chi squared is data minus the model over the uncertainty. And people often use what's called a reduced chi squared. So they take the chi squared, they divide it by n, which is the number of data points, minus little n, where n is the number of parameters, so the size of the x vector, minus 1. So this is what people often do. They try to minimize the reduced chi squared to get the most probable value of x. So in this example, yeah, so here's, again, the asterisks are the data, the error bars are the reported uncertainties, and the diamonds are the model. So in this case, this is a fake data set that I generated, and it meets all those assumptions. So this really is the best thing to do. If you minimize the chi squared, you can get the best set of parameters. But I have now will show you some data sets that I generated and then some real examples for the literature where one or more of these assumptions is violated. And then we're going to want to adjust our likelihood function to compensate for that. OK, so here's an example where one or more assumption is violated. And I want us to discuss among ourselves what assumption that might be. So I'll give you a few, like half a minute or so to think about it. And I'm going to erase the rest of the board while you're doing that. And after we talk about this example, we can do the break.
K is time.
K is the data point number. So there's also a T of K. The data is not necessarily equally spaced. So there's always a reported time, and we're assuming that there's no uncertainty in that reported time. In this case, I think I did evenly space the data points, but that's not going to be true in a real data set because of observing limitations for the radial velocity technique. Yeah, so what assumptions might be violated with this data set?
So there's more variation in the beginning than at the end, maybe?
I think that's just an illusion.
Okay.
But I think you're on the right track. There's something about uncertainties that might be a bit wonky. Other assumptions that might be violated?
They are not independent.
That they're not independent. In this case, they are independent. But hold on to that thought. I'll give you a hint that maybe we should amend this to being correctly known. So assuming all these other assumptions hold, that they're independent and Gaussian, which this is the first example of something I generated, I can tell you that's true, then what do you notice? Like if I drew a sine wave through this data set, like would it look like it's an adequate match to our data? I kind of wish I had done that, but if you imagine this kind of sine wave going through these data points, if they're Gaussian, then a lot of them should go through the data points. There should be some number of outliers, but yeah. So does anyone want to complete that thought?
Some Habital error.
Wait, say it again.
Some Habital's error. Like non-Gaussian error.
Yeah, so in this case, the error is Gaussian, but they're just too small. Like, I used some very large uncertainty to generate this that was Gaussian and independent, but it was not the uncertainty that I put on the error bar. And that can be a big problem in your real data set because as people are asking about, they give us some uncertainty, but that's usually just based on their knowledge of how precisely they can measure those spectral lines. There may be other uncertainty that they're not capturing there. And of course, it may not be independent and Gaussian, but even if it is, it might just be underestimated. So an example of that is this planet. You can see here's the model in black, and here's the data as points. It has two planets, so that's why there's sort of a long signal and then a short one. And this non-sinusoidal dip would imply that it's a planet on a very elliptical orbit. But you can also kind of see that we don't have a lot of data points where the part of the signal that shows that it's elliptical is. So there was some originally reported uncertainty, but then Payne and Ford being Eric, who taught this last week, did an MCMC analysis of the system where they had this extra jitter parameter that's added in quadrature to each of these. And then depending on how high that jitter ends up being, you can either constrain the eccentricity really well, or if there's a lot more uncertainty beyond what's reported for these data points, maybe you're really not constraining what the eccentricity is. Maybe you're not really able to measure the shape all that well. So this was a case where modifying the likelihood function in a way I'll show you when we get back to include this extra jitter term was important because it made them realize that the results aren't as precise as you might have thought if you just use the reported uncertainties. So let's have the break and then we'll come back and look at some more. And I will also tell you how to modify the likelihood function to add this jitter term.
And also, do you need that uniform prior assumption? If you do not do the Bayesian one, if you do frequencies, then you can just maximize the likelihood assuming Gaussian. The same thing, right?
So it's true. If you're doing it a frequentist approach, then you're sort of implicitly assuming, but like you don't have to select a prior.
Yeah.
But that might be a weakness there, or you might, you might need to do something to fix that if you really do want to use the prior information. Welcome back. So, as we were discussing, here the error bars have been underestimated. So one thing that we can do to fix that is in our likelihood function, this is like the simplest possible fix, but it's better than nothing. Add in quadrature this extra term that we sometimes call a jitter term, because sometimes what's actually physically going on is that our model doesn't include another physical process, which is that there's actually random stuff going on the star that's contributing to this scatter beyond just the measurement uncertainty. So just adding this to the likelihood function is really simple, but it's better than nothing because now we can get better uncertainty intervals. I was talking to David during the break that this may not be an example that comes up so much in statistics because you might always assume that the model isn't perfect and that there can be some scatter of the points around the model. So in this case, that really is what's going on, is that this is a fake data set that I generated, but here, what they think really is going on is that there's some piece of the model is missing, which is that there's random noise being caused by the star that also needs to be taken into account. Is there anything you want to add?
I guess just going back to that other figure. So you would say that the errors look too small because you would expect that that effectively the measurement error is the only thing keeping those points from falling exactly on the sine curve.
Yes.
So I think, typically like most problems that statisticians would deal with, there's sort of like a random error that's just included as a part of the model. So this might not necessarily jump out as looking wrong because you can say, well, there's some measurement error on the points, but then there's also just some like stochastic variation that we would normally expect when we are working with data.
Yeah, so that's a good distinction.
To know that the measurement errors are too small, you have to know that the point should lie exactly along the line, along the curve, except for the measurement error.
Yeah, and one important piece of it is that this, like the physical process driving this is really simple. It's a Keplerian orbit. So we do really expect this to like if we had no measurement errors, to perfectly follow that sinusoid, unless there's something like the stellar jitter going on that's interfering with that. Okay, so here's another example, particularly in light of the discussion we just had where we really expect everything to fall on the sinusoid except for the measurement errors. What assumption does this fake data set violate? Of these assumptions.
Independence?
In this case, they are independent.
Outliers.
Yes, that's right, that there's outliers. And that can be a huge problem in time series data sets that we, as astronomers, sometimes try to sweep under the rug, is that there can be big outliers. Here's an example where they fit this planet as having an elliptical orbit, which you can tell because it's not a sinusoid, it's sort of sharp. So they were like, it must be an elliptical orbit. But it turned out that this point was an outlier. And when they went back a few years later to the observing records, they saw that there had been clouds or some other reason where it was a good idea just to totally throw out that point. And then with their new fit, this is their new fit, it's no longer elliptical. Now a sinusoid is a good fit because they removed that one outlier. So that can definitely be a problem for these data sets. And one way to deal with that is to have a model where some of your data is bad or has an inflated uncertainty. So you can say the likelihood is, oops. Sorry, squared. So what this outlier formulation is saying is that some fraction beta of your data has a much larger uncertainty. Its uncertainty is inflated by gamma. That should be, squared. So instead of having an uncertainty of sigma, it's an uncertainty of gamma times sigma, and then the rest of your data is okay. And you can use this likelihood function without necessarily knowing which data point. You don't have to assign each data point as being an outlier or not an outlier. You can put your data into this likelihood and account for the fact that you may have some data that has much larger uncertainties than what's reported. So there's other outlier rejection schemes, but this is sort of the most simple way that I think I've seen for people to modify the likelihood function to deal with the outliers.
You're fitting the betas in there?
Yeah, so beta and gamma are free parameters there. Yeah. Okay. Here's an example where, so I'll give you a moment to look at it. Maybe think about how, like, all of you, this was like an interesting difference between my exoplanet astronomy class. You were all like really carefully looking at the orbital periods of your planets. So take a look at this one and see if you have a sense of what could be wrong here.
Two different times is there?
It's again, the black points are the data and the red is the model.
Yeah, I'm just talking.
Oh, like, are there two different time scales? Oh, like maybe there's two planets there. Yeah, so that's, since I made this data set, that's not what's going on here, but that actually can be a real issue. If you have other planets in the data set and you're not accounting for them, that could really mess up your inference. And one place where that's come up is, again, with following up those planets that are transiting using the radial velocity method. You saw the transiting planets, but if some of the other planets are slightly off the plane, they won't be transiting, but they will be in the radial velocity data set. And if you don't model those ones as well, which is difficult because they might be sort of right near what you can detect, then your inferences about the planet that you know could be wrong because there's some physical process that you're really not modeling that's actually happening. So that, it turns out that it's not happening here because this is a fake data set that I made, but it certainly does happen in real data sets. Yeah, so what about this? Yes.
The orbital period is too small?
Yeah, so it turns out if this were actually the orbital period, the planet would be orbiting inside its sun. Like, this corresponds to, well, oh yeah, just to remind you, since I know you're not all astronomers, separation and orbital period scale together. So the shorter the orbital period, the closer you are to the star. And it turns out this orbital period would put you inside the star. So here, this is a case that I would say violates the assumption of a uniform prior, and that you should not have let the period be this small. And what this data set actually is that there's no planet in here I actually just drew from the noise, and then I did the best fit planet. So if you do a best fit, you can find some sine wave that goes through this, even though it's actually just random Gaussian noise. And in this case, you get this amplitude, but you should have known that that period is not correct. This also gets into the issue of what does it mean to actually detect a planet? Would this have fallen into the detect category? But there are actually real-life examples where you should put a prior on the orbital period. And here is an example. So you might remember that one of the data sets I gave you to look at was in the frequency domain, and it had a bunch of peaks. And I talked to some of you about it, that those peaks are actually from, oh yeah, can you just hold it up to remind people? Yeah, that one. All those peaks are coming from the same planet. Yeah, that's fine, you can put it down. Oh, okay. All those peaks are coming from the same planet. They're aliases that are caused by gaps in the time sampling. And it's a big problem if you have aliases. You see a bunch of peaks in your Fourier transform and you don't know which one's the planet and which are just aliases of the planet signal. So that's something that's actually a big part of my own research, and I'm not going to talk about it a lot today. But this is a case where it came up in the literature where there were 2 peaks in their periodogram that were aliases of each other. One peak that was near 1 day and one that was near 6 days. And normally people would go with this 6-day peak because it's a little bit of a better fit to the data. Though that again goes back to the like, is this really a better fit or did you just underestimate the noise? But normally people would choose this one because it's a better fit. And maybe you think it would be a big coincidence to have a period so close to 1 day because the aliasing is a 1 cycle per day alias that's caused by the fact that you can only observe the star during the nighttime. But it turns out they already had found another planet in the system, and that if they went with this period, this planet would be so close to that other known planet that the system would go gravitationally unstable in just a short amount of time. So because of that, they went with this orbital period. And this is sort of equivalent to saying we should put a prior to rule out the periods that would be unstable with the planets that we know about. So in practice, what we can do if we have any sort of prior is to modify our likelihood function to include that prior, the probability of x, our parameter. And so if you're doing something like MCMC, it's easy to just build that in as you're exploring parameter space. Okay, so then the final example, which will lead into the final part of the class, what assumption is being violated here? Maybe one that hasn't come up yet.
Independence.
Yeah, so we can, yeah, but can you sort of see that by looking at it, that if we really believe that there's the true thing going on is actually a sinusoid, that these deviations from the sinusoid are correlated with each other. Like these ones are all too high, these ones are all too low. So there's some underlying physical process happening, maybe with the instrument or maybe on the star, that's causing the deviations from the sinusoid to not be independent and random.
It looks like you sampled a lot more for this picture. It looks like there's more points in this picture. Is that true? Or maybe like you would just need to see a lot more points before you actually started to see something.
Yeah, I very well might have. I don't remember, but it's a good point that depending on the time scale of the correlation, you may need more sampling to be able to characterize it really well. And that's actually one really nice advantage of transit data sets, which is what we're about to talk about, is that a lot of the transit data sets have an observation taken every 30 minutes. So there's continuously for several years, So there's a lot of data to characterize what might be going on with the correlations. So here's a real life example, Kepler 91b. So this is at transit. You can see like the little dips. This is no longer a radial velocity light curve. And when they didn't account for the correlations, the correlated noise going on caused by a process on the star, they ended up getting the wrong parameters for the planet. And they were so wrong that they assumed that it couldn't actually be a planet because those parameters just would make no sense. But then once they used a Gaussian process, which I'll talk about within their likelihood function, they were able to capture that correlation and be able to get parameters for the planet that did make sense. And then they realized that it was a planet after all, even though before they thought it was a false positive. That leads into the final part of the class. Actually, I'm just going to lead in a little bit more by discussing how we could modify the likelihood function. So we could modify the likelihood function such that we replace the chi-squared with this. So now we have defined the chi-squared so that it includes a correlation matrix that tells us the correlations in the uncertainties between each data point. So if it were uncorrelated noise, then you would only have this on the diagonals. So C k of k prime would equal sigma k prime squared when k equals to k prime, so on the diagonals, and it equals 0 on the rest of the matrix. So if you just filled this in with diagonals, that would be the same as this chi-squared right here. But if you have correlations, then you'll also have some off-diagonal terms. And the way that astronomers have been using Gaussian processes is basically as a prescription to define what these off-diagonal terms should be. So that's what I'll be talking about in this final part of the class. Let me see how much time we have. Yeah, we have time. Okay. So in the rest of the class, I'll be focusing on the transit technique, which, to remind you, is where you have the planet blocking the light from the star gets dimmer, we can measure the planet size, and we can measure the central transit time that can tell us about disturbances from other planets in the system. And these are discovered planets in terms of the mass versus orbital period. So this is separation from the star. Here's the solar system. Prior to 2005, we were mostly detecting Jupiters close to their stars. But now we're really starting to fill out this plot. And a lot of that is from transiting planets. In particular, from the Kepler spacecraft, which was monitoring the brightnesses of hundreds of thousands of stars. So it just looked at this one patch of sky right here. It monitored those stars for 4 years and looked for planets that were passing in front. So here's an example data set from the Kepler mission, except that this goes on for 4 years. This is just like a zoom in for tens of days. There's stellar variability happening. There's like spots and other stuff going on the stars. Here I've taken a planet signal and injected it into the time series. So you can see this would be a transit signal that we detect, but there's a lot of stuff going on the star that kind of has a similar amplitude and time scale, which makes it challenging sometimes to detect the planet if it's a pretty small planet, or even if we can detect it pretty well, then to actually get good parameters for it in the presence of all this correlated noise. So let's So people have been doing various things that I won't talk about in detail. Like Eric Feigelson has been doing a lot about actually detecting these planets, and he's been using ARMA processes to try to account for the stellar variability and better detect the planets. I have a student working on some things, but I'm not going to go into that. I want to briefly compare the types of challenges we face with the radial velocity data, which is mostly taken from the ground, and the transit data. One big difference is that with the transit data, we can measure the planet size. And with radial velocity, we measure the planet mass. In terms of the time series challenge, with the transit data set, the planet has a low duty cycle. Most of the time, we're just looking at the star. It's only at a special time during the transit that we actually see anything happening with the planet. So we have tons of data that tells us all about what's going on with the star with no planet interfering. Whereas with the radial velocity data, the planet is always there causing a signal. So we never have like a separate data set to work with that's only telling us what's going on with the star. The percent chance that there's a planet in your data set is very high for radial velocities. And that's because we now know that planets are very common, that about half of stars or maybe even more have a planet. So chances are if you look at a star, there's going to be a planet there. It's just a matter of what its properties are. Whereas for the transit technique, since you need a special geometric alignment for the transit to happen, most stars you look at won't have a transiting planet, even if every star had a planet. In terms of data, radial velocity data may have like 100 data points. That would be like a really good data set. Transit has 100,000 or more if it's from the Kepler mission. So in terms of what's computationally feasible, this can be a challenge, particularly if you're trying to use all the out-of-transit data to study the stellar variability. The signal repetition for radial velocities, it mostly stays a constant signal, and it's not being affected by gravitational interactions with planets. There's maybe 2 systems where that's not true. But for transits, it's fairly common that there'll be disturbances between planets and that the transit time will change from transit to transit, so you're not looking for exactly the same signal every time. With our transit data sets, they're evenly spaced and continuous, but with the radial velocity, it's uneven and has gaps that can cause aliasing. So we talked about this. I'm going to skip past this to talk about, okay, so there's a lot of correlated noise in Kepler datasets for the brighter stars. For the really dim stars, the noise is dominated, it's so faint that it's just, do you know what Poisson uncertainties are? It's just the fact that we're getting a very limited amount of photons introduces intrinsic uncertainty there. But for the brighter stars, the uncertainty may be more dominated by stuff that's going on the star, like spots or flares or other things that make it not a uniform surface. So this system that I worked on, Kepler 419, which I sort of went past the science, I don't think we have time to talk about it. If you look at its power spectrum, so here's the flux versus time. This is just a segment of the 4-year data set. If you take a power spectrum, it's not white noise. It varies with frequency. And if you take a discrete correlation function, autocorrelation function, you can see that there's a periodic behavior in the data set as well. That's not caused by the planet, that's caused by the star having spots and it rotating around, and you see the same spots coming into view. So we know that this data set is not white, that it has correlated noise in it. In fact, we use the correlated noise to measure the stellar rotation period. And it has this behavior that I see in a lot of the Kepler data, where they're at low frequencies, the power spectrum looks fairly flat. Then there's sort of an f to the -2 behavior at these intermediate frequencies, and then at high frequencies it becomes white. So I think this is the white component of the noise that's just caused by the photons. So let's skip past this. So, right. Some of the reasons why there's correlated noise in the data set, there can be star spots that come in and out of view. There can be convective blue shifts, and there can be active regions on the star. So, okay. I'm now going to talk about two techniques that we use for dealing with the correlated noise, wavelet transforms, and then the Gaussian process regression that I alluded to on the board. So just for reference, this is what white noise would look like if this were a Kepler data set. It would be a flat power spectrum. This is how pink noise would look. There'd be a slope to the power spectrum. And as I mentioned, what we see is somewhere in between, so it seems to have both a white component, a correlated component, and a periodic component. So it can have all these different components at once. So now I'll talk about the wavelet transform. Here's our data set in the time domain. Here's the data set in the frequency domain using a Fourier transform. And what the Fourier transform assumes is that there's a sinusoidal signal, or at least it decomposes into sinusoids, and that the amplitude, phase, and frequency of the sinusoids are constant. So that's fine, except for our star, that may or may not be a good assumption. Like if there's spots coming in and out of view, those spots might be changing with time. So it may not be a good assumption that the phase and frequency and amplitude are all constant. You could do a transform like this, where you, so a Fourier transform, you have frequency and amplitude. You could divide up your data into different chunks and take a Fourier transform for each of those. What a wavelet transform does is that it also looks on different scales. So what it has is time and then scales, and then it finds what's the dominant frequency for different times. And what's the scale is the same as frequency. So it finds what's the dominant scale at different times. I'll show you an example and it'll be more clear. There are different families of wavelets that you can use. This one, which I think is pronounced Derbyshire wavelet, is what we often use for transit data sets because it's just really flexible and it can match all the sorts of variations that we might see. And so here's a wavelet transform using white noise. So this is, you can see scale and time, and it looks pretty random because we have white noise, but I'll show you an example where it's not white noise, where there are different dominant scales at different times. So here's pink 1/f noise. So since there's more power at low frequencies, then we'll see more power on scales that are larger. And so the way that this is used in praxis for fitting the data set is that instead of using the likelihood function out there, we transform in the time series into the wavelet domain and then use that inside the likelihood. And then if you assume that the noise takes a form, the power spectrum has a form of 1/f to the gamma, then you can have these parameters, the white component of the noise and the red component of the noise, where you can know what it is on different scales based on this gamma relationship. So basically what this is trying to do is to say, what should the noise be on all these different scales? And what you could do is have a different noise parameter for each scale. So you'd have 8 or however number of scales there are. But in order to reduce the number of parameters, we often assume that the relationship is 1 over f to the gamma, and then that dictates how much power there is on all these different scales, except for a normalization. So that's how people use the wavelet transform inside the likelihood to fit data sets. And for a long time, like since 2009 to maybe a few years ago, this was the predominant way people were taking into account correlated noise, if they did so at all. More recently, people have been trying to use Gaussian process regression. So in this case, as I talked about, we're trying to develop a recipe for the covariance matrix. So if we just had white noise, the covariance matrix would look like this. You would just be correlated only when the time is equal to each other. So you'd only have uncertainty on the diagonal. A lot of times we use a radial kernel. So a kernel defines what this structure looks like. So what this is saying is, yes, you're correlated with yourself, but you're also correlated with nearby things, and that there's some scale over which the correlation falls off. So I don't remember why I chose this complicated one as an example. The really simple example would be an exponential kernel. So it just dies off exponentially. This one is a little more complicated, and I think the reason I chose it is that this is the one that I tend to use for transits because it seems to perform better for reasons that must be telling us something about the underlying noise process, but that I wouldn't have been able to predict in advance. So having a radial kernel is helpful. And what I did that somewhat convinced me that this would be a reasonable kernel to use is that I used the Gaussian process to generate, I used the Matern kernel to generate this Gaussian process, so this flux versus time. Then I took the Fourier transform, and it had the same behavior as I saw in the real data sets, where it was flat, then it had an f to the -2 slope, and then it was flat again. So if that's what the real data is doing, and that's what this type of kernel prescription generates, then that seems like it might be a reasonable model. And it's definitely a very flexible model. You can also have a periodic covariance matrix where, say, you're related to things a rotation period away from you. So that can be good if you have a rotating star that has spots, and then that's a big source of noise. So as I talked about before, so this is the likelihood with uncorrelated noise. You can rewrite it in matrix form, and if there's no correlated noise, you only have power on the diagonals, as we talked about. So this is what it would look like for white noise. But if you don't have white noise, then this kernel gives you a prescription for what the off-diagonal terms should be. And then you can just substitute that into your likelihood function. So you can combine different kernels. This is a non-astronomical example. This is CO2 versus year. But they use this combination of kernels to fit it, where they have an exponential piece that's fitting sort of the long-range trend that you see right here, the global warming. They have a periodic piece, which is fitting these wiggly bits. Not fitting, but taking it into account. And then they have a white noise piece that there's just some random scatter about that. So the same thing we could use for fitting our exoplanet data. And indeed, we do use that, and it works pretty well. The big disadvantage is that it's very computationally intensive because you have to factor this matrix every time you generate a new step in your MCMC, every time you're comparing the model to the data. So there's been work on trying to speed up that factorization by assuming that it's a sparse matrix so that there may be stuff near the diagonals, but there's not stuff all the way on the edge. So people have been able to speed it up a bit, but it's still a lot more computationally intensive than using the wavelet technique, and it's quite more computationally intensive than using just assuming that there's white noise. I believe that's one of the reasons that people don't always use one of these. I would say, like, if you look at planets that have been found by transits that like had their own paper written about them, maybe a few % of those papers would use any sort of correlated noise technique at all. And there's just a couple examples of people using this Gaussian process regression likelihood, but it's becoming more and more popular. So I think that number will change as more people start to realize that this is important, particularly if you have a star where it's not faint, it's bright, so you really have to take into account what's going on the star. What I didn't talk about is that with one planet data set that I was working with, I compared the Gaussian process regression likelihood and the wavelet likelihood, and they both gave similar results for the planet properties. They were different from just assuming white noise, but they both seemed to do a comparable job in getting the planet properties while accounting for the correlated noise. So it may not really matter what correlated noise approach you use. You're still going to have a big improvement over using nothing at all, provided that you're looking at a brighter star. So what are we doing for on time? Okay, we have some time left. So one question that I posed to my astronomy students that you might be interested in answering is, for these techniques, oh wait, no, we're still going to do that. Okay, for these techniques, would they be better suited for a radial velocity data set or for a transit data set? Because we talked a bit about how those are different. So let's start with wavelets. Do you think that they've mostly been used for, actually, let me actually tell you what these two are, and then I'll pose this for some other examples. So wavelets have mostly been used for transits. I believe that's because most of the wavelet transforms that we've been using assume evenly spaced data. I have seen some wavelet transforms that you can use on unevenly spaced data. For example, I applied that to this data set, and you can see there's a dominant frequency that's changing over time, which I think is due to the fact that there's, this is a little complicated, but there's spots on the star, and the exact period of the star depends on how high up they are in the star, and the spots are moving up on the star over time. So the dominant frequency in the data set that's caused by the stellar spots, not by the planet, is changing. Gaussian process regression has been used for both transits and radial velocities. And the nice thing is that you can model that there might be some underlying Gaussian process, and then you can sample that at your observation time, so you don't have to assume that you have unevenly spaced data. So there are some people working here at SAMC, like Eric Ford. Are you involved with this? Yeah, so David is also involved with this, trying to better fit radial velocity data using a Gaussian process that's supposed to be modeling the underlying stellar activity. So this has been used for both. Before these became popular, people were using some iffy methods of dealing with the correlated noise. One was called the time averaging method. So they assumed that basically that if there was only white noise and you took a bunch of data points, that your precision would improve with square root of n, where n is the number of data points. That if you have a red noise component, that would add a constant term that wouldn't go away as you got more data. And so what they did was to look at the standard deviation as a function of the number of measurements, and then fit this sort of function to it. The trouble is that this doesn't really seem to work with this assumption doesn't really seem to hold with real data sets, so it was causing an underestimate of the uncertainties, and it didn't really end up working that well.
So the white noise isn't really going away as fast as they thought?
I think the problem was that they had uneven sampling, and they didn't have any planet-free data, so this standard deviation as a function of number of measurements that was like after they removed out their best fit planet, and then they looked at this, but they had no, because this was applied to the radial velocity method, they had no data that was planet-free. So these residuals don't necessarily reflect the planet-free process, since a planet has been modeled out with one assumed set of parameters. So I believe that that's why it wasn't working as well as they hoped. It could also be that it's just not, that maybe this red noise is not stationary either. There's different hypotheses for why that wasn't really working. Sometimes people used the residual permutation method. These are sort of like fake posterior distributions of different planet parameters, where what they did is they had a best fit model, they subtracted it off their data set, then they scrambled the residuals, added them back in, fitted again, scrambled it, fitted again, and that's how they got this fake posterior distribution. The problem is that this doesn't preserve the correlated noise at all, because you're just scrambling the residuals. And so this also led to underestimated uncertainties. So this was used for both transits and radial velocities.
So for this is some kind of bootstrapping, I guess.
Yes, it is. It's a type of bootstrapping, and I believe it also
No, the bootstrapping is also bootstrapping works for correlated data, but you have to do blocking first.
Yes, that is a very good point. There's one paper I'm aware of that really trashed this method, and that's what they suggested as an alternative, is to use blocks. And they basically said that the assumptions that make bootstrapping true don't really hold if you're doing residual permutation, that there's just no statistical basis to be doing that, because they're not drawing with replacement, they're just scrambling. So that with real bootstrapping, you'd have to be drawing with replacement. But
when you are doing with replacement bootstrapping, then you are assuming that the underlying data is independent.
Yes.
So
But as you say, you could use blocks. Where you take different blocks of data and you scramble, or you don't scramble, but you draw with replacement those blocks.
The blocks. You are just collecting the blocks with replacement.
Yes. I think the challenge is that since we don't always know the underlying timescales, it can be difficult to choose the proper size of the blocks. But I think that should work in principle, and at least it wouldn't violate a lot of these. It wouldn't be a terrible thing to do, like the scrambling that's being done here.
But I think there are some papers where they show that that this kind of independent bootstrapping that can go pretty wrong.
Yes.
When the data is correlated.
Yes. So I think the lesson we must draw is just don't do this with exoplanet data. But it was really popular back in the last decade, I guess I can say. Then we still have a little bit of time. One final thing that they did was to take the radial velocities and look at other diagnostics of the star and try to correlate them. One example of that is that, so you're looking at the spectra of the star and you're looking for the lines to shift back and forth due to the Doppler motion. That Doppler motion should not be changing the widths of the lines. if something's changing the widths of the lines, that must be some other physical process that's unrelated to the planet. So they would measure the widths of these lines and then see if subtract out if there's any correlation between the width and the Doppler shift. Subtract that off from the data set or divide it out and look at the data set that way. So that's not really the most robust way to do it. What people are doing now, like the project with Eric and David, is to have the underlying Gaussian process also be affecting this, and then actually be fitting these width changes instead of just assuming that there's a correlation that you can divide out. But the idea behind it is robust. Just the way that it was implemented in the past wasn't really the best. And then finally, sometimes people, sorry, this is a little complicated. So they add to their actual physical model, not just the planet, but other signals that can have some correlation piece. Like here, what they've done is to put an exponential decay in the model itself that would be modeling some sort of exponentially decaying process that's unrelated to the planet. So that's been another approach that people have used, and it's been, I would say, moderately successful. It's definitely better than doing nothing at all. So I've been comparing different approaches for measuring central transit times really well. But I'll leave you with the summary that there have been huge instrumental advances enabling the exoplanet revolution. The fact that we now have, a couple decades ago we had no planets, now we have thousands of planets, and there have been huge leaps as the instruments have gotten better. But there's still statistical challenges that remain in order for us to really use the data to achieve the full scientific potential. It can be challenging for both transits and radial velocities to disentangle the planet signal from stuff that's going on the star that's not related to the planet. That's what people fear is going to be the biggest obstacle to being able to detect something like the Earth around a star like the Sun. But people are working on it. And that treating correlated noise in the likelihood function is essential for getting out the science that we need, at least on the brighter targets where it's not just dominated by the faintness of the star. So that was a little bit of a whirlwind in the last part of the talk. We have a few minutes for any extra questions that people have. Let me see exactly how long. We have 7 minutes for questions.
What are some of the open methodological questions that you're working with in time series, I guess?
Yeah, so a few of them. One is relates to the outliers that we talked about. That's one way to deal with outliers, but there's a lot of work going on, for example, in the SAMSE's time series group of trying other methods for either determining when you should reject an outlier or better incorporating the outliers. And that's one of the biggest concerns that I hear from exoplanet observers, particularly for the radial velocity method, that there's sort of a problem where, I guess there's sort of two competing problems. One problem is that there have been planets published that turned out not to be real, that were later retracted. Usually, though, that's been because a stellar activity signal has masqueraded as a planet. Sort of a complementary problem is that people, partly because of that, are really conservative in publishing planets. And so there are other people, probably the majority of astronomers, who wait until they have an amazing signal, like it's hundreds of sigma and it's super clear before they publish because they're just so worried that they might be wrong. And some of us have said that if we better deal with the correlated noise in the data set and use more robust statistical techniques, then we can maybe detect planets that are lower mass and have a weaker signal, or we can detect them with less data and people don't have to wait for the whopping signal to publish. But observers have been very resistant to that, I think partly because of these defrauded planets. Though I have to give the caveat that it's those planets, it's not that they didn't have a big signal, it was that the signal that they saw wasn't caused by a planet, it was caused by something else. So people are a little bit not able to distinguish those things. But the other thing I hear from observers is like, well, we can never be sure because there are all these outliers, like who knows how that's affecting the fit. So we just have to collect tons and tons and tons of data and hope that that will make us be robust to the outliers. But if there are a better way to deal with outliers, then they may be able to publish planets that are less strong of a signal or where they have less data. And then that's really useful for a lot of us here for the exoplanet part also work on studying populations of exoplanets, like what are the typical orbital properties and masses and what do they tell us about formation. And for us, the more published planets, the better. Even if it's sort of an uncertain planet, we'd rather have that uncertain planet with an accurate uncertainty and be able to put it into the population study than not to have the planet at all. But people are being so careful before publishing the planet that we don't necessarily have some of those more marginal cases. And outliers are one reason that people are concerned about that. So that's an issue. Another issue that I'm working on is just is there a best correlated noise technique among those that I mentioned, like the Gaussian process approach and the wavelet approach for measuring the central transit times? Because I'm very interested in those because they tell us a lot about the gravitational interactions in the system. Some people are thinking about, including me, about unevenly spaced data because a lot of the statistical techniques assume even spacing. And can they be adapted for unevenly spaced data, like the wavelet transform? I found one wavelet transform in the literature that didn't need unevenly spaced data, but there's a lot of techniques that I've seen from statisticians that sound really useful, but would just be really hard for using on a radial velocity data set because it's not evenly spaced. And I've been particularly interested in how aliasing and stellar activity can interplay with each other and cause spurious planet detections. And then some other folks have been interested in how can you use, instead of just using the shift of the center of the lines, how can you use this whole spectrum to better disentangle the planet signal from the stellar signal? Because the planet should only be shifting the lines back and forth, but a stellar signal could be broadening the lines, or it could be causing a signal that's not strictly periodic, whereas the planet signal should stay periodic and should keep its constant amplitude and phase. So it may be possible to use all this other information in the original spectrum, like this whole spectrum gets condensed into one data point, but using the actual spectrum itself to better measure the planet properties and detect planets, which would be very interesting. So, okay, well, thanks everyone. Thanks for coming. Thanks for participating in the activities. I very appreciate that. And I'll be around at SAMC all this week if anyone has science things they want to talk about.